The speaker today is Keith Noll, project scientist for the Lucy mission, planetary astronomer in the geophysics laboratory and former chief of the Planetary Systems Lab. He joined Goddard after 20 years as an astronomer at Space Telescope Institute. Without further ado, Keith.
Thank you. Is it working? I think it's working. Okay. So thank you all for inviting me here. Really grateful for the nice lunch and having some nice conversation. I want to tell you about this space mission that I'm working on. It's called Lucy, and we just had our first encounter with an object in the solar system, a small asteroid that named Lagrangian, last November. And it's a really fun story. So let me tell you a little bit about Lucy, and then I'll tell you about Lagrangian. So here's our mission team at Cape Canaveral. There's our PI. It's a discovery mission, which is the smallest of the competed planetary missions, and that's a PI-led mission. So that's Hal Levison. He is at Southwest Research Institute in Boulder, Colorado. I don't understand the phone but it's in here. We'll come back here. This was 14 hours before launch, afternoon, and then the next morning before dawn we launched. We're on top of an Atlas V 401 booster, one of the last of those on planetary. So how did Lucy get its name? It's named after the Lucy fossil, which Donald Hansen, you can see there, found in 1974. As I was telling folks at the table I was at, they were playing Lucy in the Sky with Diamonds at the camp, and somebody said, hey, instead of doing it the usual long string of numbers and letters, scientific name was called Lucy, and that stuck. So it's the Lucy fossil. And the reason that name was selected is that you think of the Trojan Asteroids, which are the primary target for this mission, as similar in a way that they're the lucky few survivors that we're able to get to, and they've been preserved in these stable orbits ahead of and behind Jupiter for the last 4 billion years. So that's the analogy. And there's our patch. The first is the Trojans, and you can see the really large solar arrays and the Lucy fossil there. Okay, so what are the Trojan asteroids? In case you don't remember, these guys here are the Trojan asteroids. That's Jupiter going around. This is the asteroid belt. There's Mars, Earth, Venus, Mercury. And you can see that these little swarms of bees are trapped in Lagrange points. So this is L4 Lagrange point ahead of Jupiter and L5 behind. And the question is, how do they get trapped there? The idea used to be that they just form there along with the same material from Jupiter. But we now know, or at least we think, that the solar system's early history was much more chaotic. And that the giant planets in particular were moving around and migrating, and they disrupted the disk that the planets were forming from. And when this disruption happened, mostly by Neptune moving out into the disk was scattered everywhere. And some of those scattered objects actually were the objects that populated the Trojan asteroids. One of the clues to that is that when you look at the Trojan asteroids, they're not uniform. If they form from the same batch of material, you would expect them to be relatively uniform, but we see some subtle but significant differences in them. And so the other part of the Lucy mission concept was you can't go to just one. Because if you go to one, you'll find some interesting stuff, but you won't know if it's representative of the population, especially when you have this diverse population. So here's the trajectory that we have for the Lucy mission. We call this the pretzel diagram. It's kind of a crazy diagram. It's in a non-inertial frame, so Jupiter is just fixed here. And so if you were flying on a spacecraft above, along with Jupiter, this is what it would look like here. In fact, we just do, in an inertial space, we're just doing, nice little elliptical orbits. But we launched on the 16th of October in 2021. Went around the Earth once, had a close Earth flyby, which we were using gravity assist to boost the orbit, we get a little bit of a boost from the first gravity system, come back for a second one, and then we head out into the Trojans, and we have our second asteroid encounter with Donovan Hansen, asteroid named after Donovan Hansen, obviously. Then 4 Trojans in the L4 cloud, and back for a third and final gravity assist and encounter with our final binary pair of objects. Along the way, not part of our original plan, we came up with this idea that, hey, we can get to this one other little thing. And so that's what the story of Infinite is, and I'm going to talk about that. First, let me just show you a sort of diagram of our spacecraft. So there's the spacecraft body. These are the really large solar arrays. These, from end to end, it's about 50 feet long. So it's a sizable spacecraft, but it's mostly these solar arrays. We had some trouble deploying this one initially, which you may have read about if you follow the news. We've got it almost all the way latched on all the way. So it's being held on with the lander. If any of you have lanyards at home, that's what's holding our whole mission together. But we tested it. We think it's going to hold up. So fingers crossed, right? And then here's our instrument platform, which is up at the top of the spacecraft. And, oops, didn't need to do that. And that's a movable that helps us as we're flying by pointing. We've got a camera, we've got a spectrometer. This is a Ralph instrument built at Goddard. It's a combination color visible camera and an infrared spectrograph. We have a far infrared, it's actually a Fourier transform spectrometer called test. But because of the low brightness at the Trojans, we're basically using it as a thermometer. That's the thermometer just sticking your ear up to your forehead. We have this camera here, TTCam. It's a pair of tracking cameras that we use for navigation. And I think that's it. And we're also using the main radio antenna to do radio science. So we're going to get masses as we fly by tracking the Doppler depth of the carrier signal. Okay, so this is a cartoonish version of the targets that we originally had for the mission. And the list has been growing, but let me walk you through it. So in Euripides is the largest collisional remnant in the Trojans. So if you follow the asteroids, you know that there are these collisional families which you can detect because they have a bunch of objects that have similar orbits and look compositionally the same. So the same is true in Trojans, except this is pretty rare. This is really the only really large one that we know about. And then after we started the mission, we found a really tiny satellite, which is another hint that this thing is a compositionally evolved object. It's also the grayest object. So we hinted at the differences in the spectroscopy. This is a C-type asteroid, which is relatively spectrally neutral. Then we get to Polymelian Sean, the smallest object in our main encounter object. But it's turning out to be super interesting because we've been getting shapes for these objects by pursuing ground-based stellar occultations. So we go around to where a shadow of the object in front of a star is passing over the Earth, and you can, if you have enough telescopes set up, you can get sort of a crosscut and get a shape. This thing turns out to have sort of a hamburger shape. And that hamburger shape is not at all what we could have expected. And we also found another relatively large satellite orbiting around it during one of these occultations. So that's turned into a super interesting object too. Lucas and Horus are both very red. We think those are the most primitive of the compositionally primitive objects in the batch. And then the last object in the L5, So all these are in the L4, and we're doing all of that in 15 months. It's going to be crazy from 27 and 28. And I think in 29 I'm retiring, if I'm going to be exhausted. And then in 2033, we end the mission with this binary object, an equal mass binary. You see tons of those out in the Kuiper Belt. And this is one of the few that we see in the Trojans, but it's another hint that these objects are related. And so what are we looking for to try to verify this idea that the giant planet migration is what drove the early history of the solar system? They're not going to have labels on them. They're not going to say, I was born in the far outer disk and then got transported and captured. But there's going to be clues like, you know, what are the colors telling you about? Is it just a surface thing, or is it go through and through? Are there compositional differences that we can see? We've used AWS-T to get spectrum of this, and we see that it has some interesting features. They're weak, but it has carbonates. And we don't know what else we're going to find, right? So I expect that they'll all have very low densities. The two of the satellites we now know have, well, this one and this one both have very low densities. The densities are about 1 gram per cubic centimeter or less. So these are very low even for the low density main belt asteroids. So that's our rogues gallery. But then we have these two things that we're doing ahead of time. They're practice targets. And the first one that we always planned on doing was this asteroid belt of Hansen. But in August of 2022, people were talking and said, you know, hey, what else can we do? Well, maybe when we're going through the asteroid belt, we'll be able to get some that are kind of close. You know, maybe we can get some spectroscopy or distant images of it. So this guy, Raphael Marchal, who was working with us, he's now in Nice, France, said, oh, I got a program. I can look at, you know, every asteroid. So he went through millions of asteroids, even just one smaller than we ever thought would be interesting. He said, hey, you know what? There's this one that's going to come really, really close to Lucy, even if we do nothing, about 60,000 kilometers. So for the delta V of just a couple liters per second, we were able to divert and have a flyby. And we were still like, yeah, but it's small, it's not going to be that interesting. Why would we do it? Well, it turns out that it was a perfect opportunity to test our terminal tracking system, and that's what's illustrated in this cartoon here. The only way of doing things, the main problem you have when you're flying a spacecraft is you know where it is up and down, the left and right, but you know how far you are. And since you're heading straight forward, it's hard to do trigonometry. And so if you want to point at something as you're flying past it, you can either just be pointing and taking pictures and like, oh, I got it now. But we would like to do better, right? We don't want to waste our really short amount of time. In fact, this whole mission is 12 years, and the entire main science will be done in less than 12 hours. So we want to be able to make the most of that time. So with the terminal tracking system, it's onboard autonomous tracking and range finding, and that allows us to be able to point at the target as we go by. So that's what we wanted to test, because things like that haven't been done, but nothing as complicated as what we're doing. And this gave us the perfect opportunity because of the geometry of the encounter. So that was what finally made us say, okay, go ahead. Because, you know, you're affected by all kinds of things when you're flying spacecraft. It's going to cost money. It's going to cost fuel. People are really busy doing other things. We have the, you know, the depth of the team to do this. And we've been dealing with this solar array crisis for the last year and a half. Everybody was exhausted from that. But we did it, and thank goodness we did. So one of the first things that we had to ask is, well, you know, what do we know about this thing? It's a pretty ordinary main belt asteroid. We're just skimming the inner edge of the main asteroid belt, and that's where it is. In here, it's got low inclination. It looks like we got a spectrum from the ground early on in December of 22, and it looked like an S-type asteroid, which is an ordinary chondrite. So we can guess what the albedo is, how much light it reflects. We're guessing it must be about 700 meters. There were some other things that pointed in that direction. That was just barely big enough, we thought, to be feasible to test the terminal tracking system. So, okay, we're going to do it. But, you know, otherwise, a completely ordinary, nondescript asteroid. So here's the geometry of the encounter, and, you know, like all of our encounters, you're getting in front of the asteroid and letting it go by you, but you're traveling slower when you're out at your periax, or apoax, I mean. So you throw the spacecraft in front of the asteroid and let it pass by you. But that's very similar to the geometry, so most of our Trojan encounters are very similar to this, so that's why it's a great test. So here's the first glimpse we got of it. This is in September, early September 2023. And you just barely make that. This little dot here moving into the background of the stars. That's 2 months from the encounter time. So that's another indication of how tiny this thing is. And then here it is, here we are 2 months later. So this is not a staged photograph. This is actual photograph. The data were coming down pretty slow. This was the first chance we got to see what we were dealing with. It was not a boring little rock. And so this was a lot of fun. It was a very good day. What did we see that got us so excited? Here's the movie of the encounter. Here we are flying by. It's two things. That's really cool. Wait, what's going on with that thing back there? And oh my gosh, look at that. It's not one satellite, but it's two lobes stuck together. It's the first time we've ever seen anything like that in a satellite, contact binary satellite. I can run that again if people want to see it again. Here we go. We'll take some more looks at these things. This is really fun. We'll get a sense of the 3D-ness of the object. And this is just flying by and changing our perspective. As you can see, the thermal tracking worked fantastically well. And we didn't know this was going to have a satellite when we were coming in. And that's one of the things that could really mess up the thermal tracking. It was finding two things in one and two, but it still worked perfectly. So we are really, really happy about that. All right, let's see. Oh, it's stuck on forever. All right, let's do it part one. Okay, so here's what we saw. This is one of the closest approach images, and actually the first one that we saw in this kind of resolution. And you can see that the satellite is just right behind, and but it's clearly distinct. And we're looking almost straight down the binary here. Here's the back, the second lobe back here, just barely sticking out. But it's hard to see in this geometry. But the other things that you want to notice are these massive ridges along the equator on Dinkinesh, and this little ridge here, which is kind of interesting and suggestive. And the reason that the ridges are interesting is that we see these an awful lot of near-Earth asteroids. And we think what happens is there's some mass movement, and what happens, you either lose mass or it just goes towards the point of lowest gravity, which is here because it's spinning, right? So you get centrifugal force. So downhill is this way, towards the equator. So it's an interesting clue. Well, this might just be it's not happening. All right, so how do small asteroids scale? Well, these guys are in a very interesting size regime at about sizes of less than 5 kilometers. The radiation from the sun becomes an important factor that influences their dynamics and evolution. It does that by this thing called the York effect. And the York is just the radiation on an irregular body can either cause it to spin up or spin down. Now, something as big as the Earth, it's completely negligible. But on things this small, it can actually spin up to the point where you hit this thing called a spin barrier. It can't spin any faster without breaking apart because the gravity of the equator becomes negative. Right? So if you were standing on the equator here, the effective gravity would be less than 1, and you would, or less than 0, and you would effectively just fly off into space. Before that happens, though, these things probably break up in other ways. There's landslides, or in the case of Dinkinesh, we think what happened is what you see here. You see this prominent ridge that goes all the way around, and if you just take this piece and put it back together, kind of like Africa and South America fitting together, it's like, oh, wait a minute, this thing just sort of popped apart. And so like a ice skater spinning at maximum speed, if they just put their arms out a little bit, they'll slow down. So that is enough to stop the collapse. But meanwhile, they shed a lot of mass, goes into orbit around the thing. A bunch of it falls back as this equatorial ridge, and the rest of it maybe forms a satellite. So that's our working hypothesis. And as you can see, these are near-Earth asteroids, main belt asteroids. This is the spin period, and this is the size from up to 5 kilometers. And there's lots and lots of things that look like Dinkinesh. Dinkinesh is not a unique object in that sense. It's supposed to be a spin. It's Here's a view, close-up views of Salam. And we named the satellite Salam. Salam is another fossil, and this was named by Raphael Marchal, who identified the target in the first place. There's a fossil of the same species as Lucy, but it was a baby, and so it's often called Baby Lucy, and we thought that was the perfect name. And it means peace. So it's the first contact binary satellite, it's about 500 meters long, and we'll talk about the orbit in a little bit more. Here's another idea of the size of this thing. And when Tom Statler comes to talk to you, he'll be talking a lot about this. Didymos and Dimorphos were the targets of the DART mission. The DART spacecraft crashed into Dimorphos, changed the orbit as a test of planetary protection techniques. And this is the first time we've had an object. They're very similar in size, Dimorphos and Dinkinesh, same composition, but there's differences you can see, and especially there's differences between the satellites. It looks like Dimorphos is, basically just a regular figure, almost like a fluid. And in fact, when the Hera mission gets back to the Didymos and Dimorphos system, the damage from the impact might be completely erased because this rubble pile behaves like a fluid. It does not look like that's what's happening with Salam. It has angular features, ridges, other things going on. It has some craters. So somehow it's more coherent than Didymos, which is an interesting thing for people to explore in the future. We don't have answers to why that is, but it suggests differences that could be interesting. Here's a scale. So I said this is located in Colorado. This is Boulder, Colorado. Here's the University of Colorado Boulder there, and this is sort of the western part or the northern part of the city. So you get an idea of the scale of things, the flat iron. It's would be a bad day if that was Boulder. Right. So here's what we know. Here's what we learned about the orbit. So as we were leaving, we were watching the system every hour for 96 hours. Because from the ground, we already knew that it was a slow rotator. And after doing some analysis to separate out the signal from the rotation of the primary outfit, which rotates faster, it rotates about 3.7 hours, we could actually see that happening during the flyby, a little bit of motion. But the orbit is much too slow. It's about 53 hours. And when we piece this together, what we see is this interesting feature. So here's where Lucy was when it flew by. And then you see these events. It goes down. You get these dropouts. These are when the sun is the shadow of one of these objects, either Salam on Dinkinesh or Dinkinesh on Salam, is passing over. So these are eclipses that we're witnessing in this light curve data. And we see that again on the other side. So that confirms that that Salam is tidally locked. It's going around Dinkinesh in the configuration that you see here. And so we now know, we also know the plane of the orbit because it would have to be in the same plane as the orbit of Dinkinesh around the sun in order for these eclipses to occur. And the fact that we see them occurring is another clue. And the fact that we don't see events from Lucy means that there's another constraint on the configuration. So it's like the Earth and the Moon, essentially, right? The Moon here keeps its face pointed at the main body is rotating faster. So here's what it looks like. The other thing to notice is that this is looking down from the north, so these are rotating backwards. So retrograde, that's pretty common. You have 50-50 chance, really. You could be prograde or retrograde is not a preference necessarily. But the fact that, but they're almost always, the satellites and the rotation are in the same direction. And that's something that that configuration of the synchronous binary comes from tidal forces. So same reason the moon is pointing one face of the Earth is from tidal forces. In this case, it's the ocean, but in solid body tidal forces. The other thing we know is that the rotation pole points almost due south. And that's because this is where radiation pressure comes in. One of the things that it will do is it will flip all these systems so that you're either spinning, pointing with your spin pole pointing north or south, and not in between. So that's a pretty interesting thing. That process takes an order of a million years. Pretty fast, maybe. So here's this scenario that I was talking about earlier, what we think happened with this guy. And the simplest thing is you spin up the primary, you shed some mass and make a ring. Part of the ring falls back and you get this material ridge, and part of it forms a satellite. In this case, for some reason that we don't know, it forms a binary satellite. Or maybe that happened twice, right? You make one satellite and then a little bit later you make another satellite and they somehow get together. Or maybe you just make one satellite, but it gets spun up some way and it breaks apart and forms two. So this is 3 ways you can imagine this happening. We don't know which it was. And again, I don't know if we'll be able to tell, but that's for the next people working on this to figure it out. And here's what we're doing next. December 13th this year, we have our next flyby. Might be visible from Hawaii, we're not sure. The last one was visible from Australia, and we got telescope images of it flying from Nebraska. It's really cool to see something that you launched, something that you're standing next to in the clean room, flying off and going out to the Trojan Asteroids. So that was pretty fun. We're going to do another practice run. This time it's going to be more detailed because Dinkanesh was a terminal tracking test, so we didn't add a lot of science sequences to it. We added some, obviously, because you saw them, but not a lot. This one's going to be full just rehearsal, so we're going to treat this one just like we do one of the Trojans. And that's the test that we can put together a sequence without causing computer crashes and that sort of thing. And then, about a little more than 2 years later, we get our first Trojan flyby. When I started this mission back in like 2016, it seemed like, man, this is really a long ways away. And I'm already halfway through. And this thing happening next April seems crazy close to me. I'm like nervous about this. And then as soon as we're done with that, we're going to turn around and get ready for this one. And then we're going to get ready for 3 more in just less than a little more than a year. So it's exciting times. We're having tons of fun. And I've got a million backup slides if you guys want to ask some questions. And there you go. That's a picture I took right after lunch. Thank you. Sure.
The fact that those 2 moons that were orbiting Dinky there, they were synchronously locked like that. One of them possibly in the Lagrange L1?
They're not in the Lagrange points, but the contact binary is physically attached, right? It has to be. Because if they were 2 separate objects and satellites that kept layering shear, they would come, they wouldn't be along. So we know that they're physically attached.
So
in the images, we actually can't see the attachment point because of shadow.
Attached right now.
Yeah, they have to be. It wouldn't be dynamically stable if they weren't attached.
I didn't see any that looked like a rope.
No, I know. No. Well, no, the two lobes of the satellite are physically attached. Yeah, they're attached to each other. So it's just a bi-lobe object. You look,
Just kept trying to follow that. What did you say that is the main, summarize the main objective of this whole mission?
Well, the main objective is to test this thing, this idea, this model of early planet formation and planetary migration. And if we can find evidence that these things didn't form where they were, but came in from further out, then that would be evidence in favor of what we call the least model. But it's a model of how the early solar system formed. The least model already has a lot of successes, right? So it's this model. One of the big problems I remember when I was in graduate school is there's no way to form areas in empty. in less than 120 years. Right? No matter how massive you make the disk, form in the amount of time that you have. And these models solve that by having all the giant planets go in a much more compact configuration and then moving later. And we know that happens because we see that in exoplanets too, right? Giant planets are orbiting at the interior of Mercury. They didn't form that. So things have to be moving around. And once you get into the physics of how growing planetesimals interact with disks, they can migrate, right? And actually the real question is, how do you have to stop them? You stop them when you run out of disk. So that's what happened with Neptune. Neptune won the lottery, and it was the one that was on the exterior. There may have been more, right? We may have lost some planets, right? So in fact, it's likely that we did. But this is competition to grow, hierarchical growth, and then you get this competition for the last, oligarchic growth. So the rich get richer, and the rest get scattered away. So, as I said, I think one of the key things is going to be density. The other will be composition, if we can find evidence for a lot of volatiles. Density is an indirect way of getting that evidence, but we may also see layering in craters, which would indicate that the stuff on the surface is just dry up regolith, which it probably is. But we would like to know what the depth of that is. Does it vary with latitude? Is there more subsurface ice near the poles than near the equators of these objects, like on Mars? So those are the kinds of questions we can ask. The other ones will be, how old are the surfaces? You can get that from crater counts. One of the things I didn't talk about here is that we've been able to do crater counts on Dinkinesh and Salam, and they're only a few million years old, their surfaces. They don't have very many craters. For the small objects in this, like Dinkinesh, this is part of the life cycle. And probably all these small asteroids probably go through this life cycle many times. Expected lifetime against collision for a system like that is on the order of tens to maybe 100 million years. And in between that time, once there's a lot of things that can happen this long. The tidal get volatile all the way out, it can get stripped. There's another thing called binary warp that can cause the orbit to evolve. So probably what happens is, if you could watch these things speed up, you see these things spinning, and they form a little satellite. They exist like that for a while, and then that breaks up, and then they get spun up again, and they form another little satellite. And they're probably just clunking out these little satellites. But instead of breaking up into pieces all at once, they do it in this sort of slow motion dance, which I think is really cool.
That's representative of what may have happened in the rest of our solar system, just for flying off what you watch.
Well, this is things coming apart, right? So we're trying to, for the main goal for Lucy is we're trying to figure out how things come together. But this was, the other really cool thing about this was that from the dates, from the time we decided, or the time we learned about doing this, to the time we decided to the time we got data was only a little bit more than a year. That never happens on a space mission, right? It's 10 years at least before you think of something and first get data. So this was a wild ride from a spacecraft point of view. And I should say that we work with Lockheed, and they've been fantastic, really supportive. So, yes.
I have trouble hearing.
Yes.
Is that a trail that it left?
Yes, that's the trail from the booster.
So it's dropping and or it's affecting the atmosphere.
I guess it got twisted around from the high altitude winds as we launched before dawn, and this was right after dawn. And
it's not pretty high material.
No, it's just the exhaust from the spacecraft booster.
It's reacting with the atmosphere.
Yeah, and just getting swirled around.
It just disappeared?
Yeah, that only lasted for 30 minutes or so. It wasn't very long lasting.
Very nice.
Yeah. Well, thanks anyway. And if you want to come up to me in private and ask questions, that's fine.